So we said that there's two main types of bonds in chemistry, right? We said covalent bonds are when you share electrons between two atoms, and this occurs typically between nonmetals where there's a small difference in electronegativity. What's the other type of bond? Ionic. That's where you transfer electrons, you don't share them. We're going to be focusing on covalent bonds for the rest of today and maybe even tomorrow. But the key takeaway is being able to form these Lewis structures. So anytime I give you a molecular formula, you should be able to draw the individual atoms with their Lewis dot structures and then figure out how to pair electrons so that you have either bonding pairs or lone pairs of electrons. So the first example we did yesterday was with chlorine gas, that war weapon. And we've got a single bonding pair between the two chlorine atoms and then a bunch of lone pairs around them. Then we went into an example like ammonia, where we've got one lone pair and three bonding pairs. And then we went into methane. And then we went into some funky examples after that, where we talked about multiple covalent bonds. So in the example of oxygen, you actually have to pair up both of them, and you end up with a double bond. With nitrogen, we end up with a triple bond. And then the last one we had was another war gas, where you have a combination of double and single bonds. The key takeaway with this, too, is that typically carbon likes to be in the center of things. So anytime I give you a molecular formula and there's carbon, try to have that in the centermost portion of your molecule. What we're going to do today is talk about polar bonds and polar molecules, and then we'll get into something called VSEPR theory. So not all bonds are equal. We said some bonds tend to share electrons, others transfer electrons, and then you even have this gray area in between. So the first type of bond is a nonpolar bond. And these are always covalent. And a nonpolar covalent bond is where electrons are shared equally. Between two atoms. The easiest way to identify a nonpolar covalent bond is to basically just go to that electronegativity table that we had yesterday, take the electronegativity value for one atom and subtract it against the neighboring atom. And if that difference is small, meaning between 0 and 0.5, it's considered a nonpolar covalent bond. So small difference in electronegativity. So the difference is typically between 0 to 0.5. If it's larger than that, it's typically not shared equally. One of the atoms will win out. There are also polar covalent bonds. Where electrons are shared unequally. And these have a larger difference in electronegativity. Typically, these have a difference in electronegativity of about 0.5 to 2. So we'll do some examples with these. What do you think happens if the difference in electronegativity is greater than 2? Will it be a covalent bond anymore? It'll be an ionic bond. So let's make a note of that. If the difference in electronegativity is greater than 2, then it is ionic. So let's take some examples and then we'll refer back to that electronegativity table. So the first example I have is HCl. This is hydrochloric acid. It's the same acid that's inside your stomach. It helps you digest your food. Let's first draw the Lewis structure. And then what I want us to do is to determine whether or not this bond will be polar covalent or non-polar covalent. So how many valence electrons should hydrogen have? 1. Okay, and then over here I'll do chlorine in green. How many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we want to pair these up. I'm going to redraw this over here. That means we've got hydrogen covalently bound to chlorine, and the chlorine's got these leftover lone pair electrons. Okay, so that's our Lewis structure. Now we need to go back to that electronegativity table. So I'm going to go back up here. So we've got hydrogen. Its electronegativity is 2.1. Chlorine's 3.0. So which one wants electrons more? Chlorine or hydrogen? Chlorine. It's closer to that top right-hand corner. The difference in this case is 0.9, right? So let's go back and put that down. So the difference in electronegativity is 0.9, and we said that the chlorine is more electronegative than the hydrogen atom, right? So chemists like to represent this using special symbols. And I've got an example below. So the chlorine essentially is going to pull electron density away from that hydrogen. And so we use this delta symbol. So can you see this delta negative right here? Delta negative means it is hogging electrons. So the cheesy example in the book is chlorine's stealing the blanket out of the bed. So it's stealing that electron density away from the hydrogen. Yep?
Are there any properties of electronegativity, like this difference between any physical or chemical properties?
So typically, really electronegative atoms tend to have unique properties that you'll cover more in organic chemistry. But they do have very special properties. It's a little bit outside of the scope of this course, so that's a good question. And then we've got this delta positive symbol for the hydrogen over here, where delta positive means it is electron deficient. There's also another way of showing this. So you can use the delta symbols, or you can use arrow notation. So if you use arrow notation, all you want to do is have an arrow pointing in the direction where the electrons are being pulled. But then at the tail end, you want to kind of make a cross mark. And the way I remember this is at this end looks like a plus sign. So this is partial positive. And then over here, that's where the electrons are being pulled to. So this one's partial negative. You can represent these either way. If you go on in chemistry, you'll see them written both ways interchangeably all the time. So I'm fine with it, but I do want you guys to know what that delta positive versus delta negative means. It's used anytime you have a polar covalent bond. If you have a non-polar covalent bond, things are being shared evenly and you don't have to use a delta positive or delta negative. Does that make sense? Let's do another one.
So would that one be polar?
Yes, so this would be a polar covalent bond because that delta En, or the difference in electronegativity, is 0.9. So it's greater than 0.5. Let's do another one. Let's do... I'm trying to think of a good one. Let's do NH3 again. So ammonia. So nitrogen is probably going to be in the center. It's the largest atom. We've got 3 hydrogens. And then we need to figure out how to piece them all together. We know hydrogen has 1 valence electron. Nitrogen has how many again? 5. So this was one we did yesterday. Okay, so if we go ahead and we draw the Lewis dot structure, we've got bonding pairs between the nitrogen and hydrogen, and then a lone pair left over. Okay, so if we look at this one, again, we can go back to that electronegativity table, and we can say, what's the difference between nitrogen and nitrogen and hydrogen? Excuse me. So again, it's 3.0 and 2.1. We're at a difference of 0.9, and that nitrogen's a lot more electronegative. So if we go back, we can say very clearly the delta En is 0.9. That means it's polar covalent bonds. Now what we need to do is we need to indicate all of the dipoles by using either arrows or that notation, right? So what we can do is we can say, all right, this nitrogen is pulling electron density away from that hydrogen. It's also pulling electron density away from that hydrogen. And it's pulling electron density away from that hydrogen. So you can actually show 3 different arrows. Have any of you guys taken physics yet? A couple people? Have you guys talked about vectors at all?
All the time.
Yeah, all the time. So dipoles are vectors, which means you can actually add them together in a mathematical way, and they'll average out depending on the strength of the dipole. If you go on and you take physics, you'll talk about vectors in a lot more detail, but this is an example of that. Let's do one last one. Yep.
Can you say it again, how you have an arrows, like which way you know how to point it?
Yeah, so the arrow always points towards the more electronegative atom. So in this case, nitrogen's more electronegative than hydrogen. So all 3 of these arrows are going to be pointed towards the nitrogen. It's hogging electron density away from those hydrogens. Okay, so let's do one last one, and this one's a little bit more complicated, although it appears easy. Let's do our classic one. We'll do H2O. So we know we've got hydrogen. We know we've got oxygen, and we know we've got hydrogen. Hydrogen has 1 valence. Oxygen has 6. Okay, so we can go ahead and pair these up. Pair these up, not too bad. Does that look good? Did anybody draw it differently? How did you draw it?
In the top, the left, top left, the top and the right, the 2, and then the hydrogens are close to each other.
Okay, so the hydrogens are close to each other. So you drew it this way then, right? So then the question is, well, which one of these is more correct? The answer is a little bit complicated, and we're going to get to that next. But let's include the dipole arrows. What do you think is more electronegative, oxygen or hydrogen? Oxygen. So we could say, all right, so each of these arrows is going to be pointing towards the oxygen. Now the question is, which is a better representation? Does anybody know? Top or bottom? Think about it this way. If we look at the top one, those 2 arrows are kind of canceling each other out, right? Because of symmetry. Where on the bottom one, we've actually got both of them kind of pointed in that same direction, going this way. In this case, water has what we call a net dipole, which means the overall molecule has an imbalance of electron density. So really the bottom one's a slightly more appropriate way of drawing water. But it's not super intuitive, and we actually have to practice this a fair amount. And that leads to the next topic of VSEPR theory. So the first thing I wanted to talk about was that Lewis structures don't describe shape very well. And the example we just saw was water, where we said, should we draw water like this. If we draw it like this, that implies that this angle is 180 degrees, right? Experimentally, we know that this actually isn't the case at all. We know that this angle is actually closer to about 104 degrees. And this is due to something called the valence shell electron repulsion theory, or VSEPR. It's a mouthful. And what I want you guys to do, if you haven't already, is to grab this handout up front, and I'll kind of walk you through how to interpret what VSEPR theory means. Does anybody need one? Anybody else need one? Okay. So VSEPR theory is really straightforward. It basically says that electrons in space want to be as far apart from one another as possible. So let's make a little note of that. So VSEPR is the valence shell electron pair repulsion. And the quick and dirty part is that electrons in the valence shell both bonding and non-bonding will orient themselves in such a way to maximize their separation. Which makes sense, right? Electrons have a negative charge. Two negative charges don't want to be close to one another. They'd prefer to be as far apart from one another as possible. So this looks complicated and overwhelming, but the trend is really easy to identify. So the first thing I look at is the key. And the key says, all right, what we need to do is to determine the number of bonding and lone pair electrons around the central atom. So for example, let's say we've got a central atom right here, and we've got two bonded atoms attached to it, right? Those two bonded atoms would prefer to be as far apart from one another as possible. And then we have to describe the shape. The shape is very clearly called linear, right? Because it's a straight line, and the angle between those two outside atoms is 180 degrees. Not too bad, that makes sense, right? All right, and then if we go down, we can say, well, what happens if we have 3 electron sets around our central atom? We can do this in a couple different ways. We can do it in one way where we have 3 bonded atoms around our central atom. That's in the first box. Or we could have 2 bonded atoms right here, and then a lone pair hanging out. Either way, we still have 3 electron pairs around the central atom, right? One's non-bonding and 2 are bonding. Both of these are called Trigonal, Planar, electronic geometry. And if you have 3 atoms around your central one, that's just called plain trigonal planar. But if you do have a lone pair, typically when we're describing the overall molecule shape, we don't look at the lone pairs, we just look at the bonded atoms. And so this would be called bent right here. So the electronic geometry is different from the overall shape. Electronic geometry basically just says we've got 3 sets of electrons around our central atom. This top one before it was our linear electronic geometry. And then we've got to go to our next one. All right, so we've already done 2. We've done the third one. What happens if we have 4? This is called our tetrahedral electronic geometry. And among this tetrahedral family, we've got 3 different shapes that can come out of it. You can have one where you have 4 bonded atoms, and these are called tetrahedral. You can have one where you've got 3 bonded atoms here, here, and here, and then a lone pair. This is called trigonal pyramidal because it kind of adopts the shape of a pyramid. And then last but not least, you can have 2 lone pairs and 2 bonded electrons, and that's referred to as bent. So it's pretty straightforward. It does confuse students sometimes because they say, well, wasn't this one bent? Yes, they're both called bent because their overall shape is a bent shape. It's not linear anymore. So we're going to use this terminology a lot. The good thing for you guys is I'm going to cut this off right here. And you guys will learn this later if you take general chemistry. But we're only going to be focusing on linear electronic geometries, trigonal planar electronic geometries, or tetrahedral electronic geometries. Yep?
So is water just an exception as to it won't be linear?
Yeah, so if we go back and we do water, right? So the question is, how many pairs of electrons are around carbon? Or around oxygen, sorry. How many would we have? So we want to count pairs. 4, right? We've got 2 sets of lone pair electrons and then 2 sets of bonding. So 2 lone pairs. That means we've got 4 total. That means we're going to be in that tetrahedral subclass for electronic geometry. So if we go down here, we'd say, all right, we're going to go down till we hit 4 electron pairs around that central atom. But we know only 2 of them are bonded. The other 2 are lone pairs. So water's total shape would be described as bent. Does that make sense? Okay. All right, so what we're going to do is a little bit of practice, and I've got a worksheet for you guys that we're going to do. And this worksheet looks a little bit complicated, but the first thing I want you guys to do is to draw the Lewis dot structure for all of these. And then once you've got all of those drawn, check with your neighbor, and then we'll go through and do some of the molecular shapes. So I'm going to hand these out, and then we'll get started on human candy. I'm going to pause the recording here. Okay, so right now we're just working on the Lewis structure portion, not the whole thing. So the first one, we've got CCl4. This is carbon tetrachloride. So what do you think the central atom is going to be? Carbon, it says so. All right. So we'll go ahead and we'll say, all right, carbon normally has 4 valence electrons, so I'll put those out. We've got 4 chlorines, so I'll try to space them around evenly because we know VSEPR theory says they want to be away from one another. How many valence for each chlorine? 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, now we want to pair up our unpaired electrons. Got one there, one there, one there, and one there. Okay, so now all we need to do is turn those into lines. So I'm just going to erase this real quick. And we would say, okay, carbon with 4 bound chlorines. Yep. No, I just want to be able to clearly see your single versus double versus triple bonds, for example. So I typically will draw it like this. Does that make sense? Okay, let's do the next one. The next one's a little bit trickier. It says carbon and oxygen are the central atoms. So I'm going to put those right here and right here. Okay, it looks like the carbon has 3 hydrogens bound to it. It says H3 in the beginning. So I'll put 3 hydrogens out here, here, and here. And then oxygen has 1 hydrogen. Okay? So now we need to put in our valence electrons. Carbon again has 4. Hydrogen has 1. Hydrogen has 1. Okay, so immediately we can say these are going to be covalent bonds. You're probably noticing hydrogen always forms single bonds, never double or triple bonds. And then let's go to oxygen. Oxygen normally has 6. And then this hydrogen over here normally has 1. So we compare all of these together into bonding sets, right? So if we go ahead and redraw this, I'm going to erase it. We should have hydrogen down to carbon, oxygen, and then hydrogen. This is called methanol. It's used as a fuel for drag racing cars, and it's also used in the production of plastics. You guys want to try the next ones, or do you guys feel comfortable working through it on your own a little bit more? All right, let's do a little bit more practice. The first two that we did were the carbon tetrachloride and methanol. Those were pretty straightforward. Some of the other ones get a little bit more complicated. We already did water. That one's pretty straightforward. With phosphorus, we do have a lone pair on phosphorus, so we have to account for that. So this would be the correct Lewis structure for phosphorus trichloride. If you guys see something that doesn't make sense, stop me. The next one's hydrogen sulfide. That's a gas produced by volcanoes. It's a poisonous gas. You guys also detected it in your iron sulfur lab. So that one looks a lot like water, where you've got 2 lone pairs. Ammonia we've already done, where nitrogen has 1 lone pair. Then if we go down here, we've got some more interesting ones. CH2O is also known as formaldehyde. This is used for embalming animals or human beings, for that matter. So if you've worked in a cadaver lab, you've probably smelled formaldehyde. In this case, we have a double bond between oxygen and carbon in order to pair up all our electrons. How many of you guys got that one? A little tricky. That's good. All right, C2H6 is ethylene. This is also found in natural gas. So in this case, we have single bonds between the carbons and between the carbons and all the hydrogens. And then down here, we've got C2H4. This is ethylene. This has a double bond between both carbons. And in this case, we have to orient the hydrogens ideally so that they're as far apart from one another as possible. And then last but not least, we've got C2H2. This is acetylene. This is used in welding torches. And in this case, I put the hydrogens kind of pointed out in order to maximize the distance between all of the atoms. Now what I'll show you guys is a cool computer simulation. And we're going to go back up to this carbon tetrachloride one. So if we look at the central atom, how many atoms and lone pairs are around carbon? 4 atoms and no lone pairs, right? Okay. So what I'm going to do is I'm going to fill this in. I'm going to say, all right, we've got 4 atoms and no lone pairs, so a total of 4. What electronic geometry matches that? Tetrahedral, okay? So it's in the tetrahedral class. Perfect. All right. For the next one, we'll do, so this one is for carbon. Let's do the same thing for chlorine, just for fun. All right, how many atoms are bonded to each chlorine? 1. How many lone pairs? 3. What's the molecular geometry? Yeah, so for chlorine, actually let's change that to electronic geometry. For the chlorine, it would be tetrahedral, although it's kind of an odd example. Now what we need to do is start talking about this molecular geometry, though. So I'm going to go back and erase this. Okay, so what we're going to do is use this computer simulation to try to represent the shape of this molecule. And then tomorrow we'll actually use model kits. So if you go on the notebook, I have this link for PhET simulations. And what we'll do is we'll try to make a model for this. And I'm just going to remove all. So let's imagine this is my central carbon atom. We've got 3 bonded chlorines, so I'll go 1, 2, 3, 4. And now what you can do is you can actually rotate it around. And if we look at this, what's the overall shape? Tetrahedral. So you can click down here and check your molecule geometry, which is tetrahedral, which in this case happens to match the electronic geometry, which is also tetrahedral. So this is a nice way to kind of manipulate and see the overall structure. So let's go ahead and fill this out. So if we're just focusing on carbon right now and not on the chlorines, we'd say there are 4 bonded atoms, 0 lone pairs. This is also tetrahedral. Molecular geometry is really just the shape. Okay, so if we do a 3D sketch, this gets a little bit trickier. What I like to do is draw my central atom. We can have 2 chlorines that are essentially in plane. But if we go back and we look at that computer simulation, let's try to match it up to this drawing. So the 2 chlorines on the left and top are in plane, right? But one of these chlorines back here is in the back and one's coming forward, so we have to represent that using a special drawing technique. And what I really like to do is for the ones sticking towards you, turn them into wedges. So this chlorine's kind of poking out at us, so we'll represent that with a wedge. The other one was kind of sticking behind us, so I'll show that with a dash. So this means pointing back. And this one means pointing forward. All right, so if you want to play around with this computer simulation, it's pretty handy. It's a good way of seeing things on the computer. But tomorrow when we come in, we're going to complete this worksheet using physical modeling kits. So make sure you come tomorrow and make sure you bring this sheet with you because we're going to continue to add on to it. All right, I think that's where we're going to stop today.